guess I should leave the batteries in.
Yeah. McKenney, he's a distinguished engineer at the IBM Linux Technology Center, where he gets to maintain part of the Linux kernel. He's been coding for 4 decades, and more than half of that has been spent on parallel hardware, doing packet radio internet protocols and system administration at SRI International, and work on real-time systems as a self-employed contractor. His hobbies are what passes for running at his age, which he says is hiking, and has the wife and grown kids habit. So with that, I'm going to go ahead and turn it over to Paul and welcome him back for the first time. And I think it was 4 years ago you spoke here. Yep. So go ahead, Paul.
Thank you, Erin. So this is a bit of a project over the past 3 years. We were hoping to get it done quite a bit faster than that, but welcome to real life. My partners in crime, John Gleb, Luke Marengay, Andrea Pear, and Alan Stern, plus there's a rather long list of Linux kernel maintainers of various types. They're joining in as well. At the beginning of last month, it was accepted in Linux kernel, so we passed that milestone. Okay, so talk a little bit about what the heck I've been doing since 2014, and you can see the other list there. We'll see how far we get. I'm much more interested in having good interaction than making it through a fixed set of slides. So if you have a question or comment anytime, please shout it out, and we'll deal with it. On the phone, of course, you should go on mute before you shout it. That makes it easier for me to hear it. Or I suppose you can, communicate otherwise to one of the people in the room that has a laptop and have them shout it out for you. Either way. So what have I been doing since November 11, 2014, when I last presented here? So this talk is about the Linux kernel memory model. We'll talk more about that. There's actually been 3 separate efforts using 2 different tools to do formal verification of significant pieces of my code in the Linux kernel, RCU. This was a bit of a surprise. There's publications. There'll be lists of those later, or in the slide set that I'll send probably to Erin later on. If you come to me and say, Paul, I formally verified your code in the Linux kernel, my response is likely to be a form of, yeah, sure. I can write printf verified too. So what I'll do is I'll give you bug-injected versions of my code and see if whatever you're doing, you find the bugs. And that's what Verification Challenge 6 is about. That was actually asked for by some formal verification researchers. It's a Git archive that has several different branches in it with different changes, some of which I believe constitute bugs, others of which should have no effect. We're working towards having RC in the C++ standard, surprisingly enough at the committee's request. And we're also refining RC in the Linux kernel. So, of course, you may have a question about that since I started working on RC in the early 90s. It was accepted in Linux kernel in 2002. I started maintaining it in 2005. How much more refinement could you possibly need?
Could you remind us what RCU stands for?
Oh, I'm sorry. Read copy update. It's a synchronization primitive. You can think of it as sort of, kind of being a reader-writer lock, except the readers don't do anything. And when I say don't do anything, I mean that a reader might execute the same sequence of machine instructions that you execute to traverse a linked structure with no parallelism whatsoever. Okay? And so the updaters have some tricks they do to make that so it doesn't blow up. Well, so on refinement, this is your elegant synchronization mechanism. All right? And you can imagine how this goes. Yeah, Mr. Torvalds, will you please accept my synchronization mechanism? Yeah, I'll look after it, I'll clean up after it, I'll feed it, all this. Problem is, if you want your synchronization mechanism to actually survive in the Linux kernel, this is not going to cut it. Instead, you're going to need something more like this. The Linux kernel can be a bit of a hostile environment to synchronization mechanisms. And every few years, somebody figures out a new way to break me, and I have to come up with ways of dealing with that. So it's they aren't even being hostile. If they were actually being hostile, it'd probably be a lot worse. So that's my goal, and I guess I've gotten a lot of way there, but there's still more work to do. So that's an ongoing task. So let's go back into this topic, the Linux kernel memory model. How many people have worked with memory models? Got a few people. Okay, good. This is an example of a litmus test. This is kind of a stylized version of it. So we have different threads, and this funny-looking stuff could appear in the Linux kernel. We have a write once, which is sort of like a C++ relaxed write, except that it has volatile semantics as well. So what that means is it's going to write the thing as a unit, and it's going to write it. It's not going to allow stuff to get written to it ahead of time, and it's not going to write it multiple times or omit the write just because there's another write later, which with the normal write, the compiler will leave its writes do all of those things. And similarly with the reads. So we have the threads. It writes to a variable, it reads to the next variable. It writes to the variable that was read, it reads from another variable, and so on. And there's a cycle. X0 is mentioned down here. And this exists clause is asking, can we get this counterintuitive result where all of the writes happened after all of the reads? And in that case, if all the reads would come back 0, 1:R1 thread, 1:1 R1 here, that's thread 1. R1 is register 1. So if is this 0, and the same thing for 2 and 0, are all of those things 0? In other words, did all these writes happen before all the reads, even though there's a cycle? The answer is, of course, we haven't told the compiler or the CPU that there's any particular ordering. We have actually told the CPU they're volatile accesses. We haven't told the compiler they are volatile accesses. We haven't said anything to the CPU. CPU is within its rights to reverse those, and in fact, a number of CPUs will very happily do that. In fact, almost all CPUs will do that. Even x86 and the IBM mainframe will be very happy to swap those around. And once you swap them around, of course, then it's totally natural that the reads might happen before the writes. And so that's the point of the Linux-Kernel memory model, to help people see what's possible, what can happen. The idea being to hopefully give them a way of working out what they can and can't get away with in their code. Hopefully mean that the Linux kernel ends up being more robust. The thing is, this all distinguishes from sequential consistency. Sequential consistency, of course, being the case where all of the threads accesses happen in order and there's just some interleaving of them, which is nice and wonderful from a theoretical perspective, they tell me. Although there is a paper that was written, or a presentation last November called Sequential Consistency Considered Harmful by some of the guys at Max Planck Institute of Software Systems. So, there's at least some pushback on that, which in my opinion is quite overdue. But what happens is that if you want your CPU to run fast, you need a store buffer, because if you do a whole pile of stores all at once, and you have to wait for the cache lines to show up in a multiprocessor, you're going to be running very slowly. If you can squirrel those away, put them in the store buffer, and keep going, you'll get a lot better performance. But the stores, at the very least, are going to be reordered with later loads. And on a lot of machines, the stores themselves may get reordered as well. ARM and Power, RISC-V, NIPS, and ITAM all allow the stores to be reordered in addition. So we've got this hardware optimization that's really important, just in case you want your code to run reasonably fast. But it causes some interesting things to happen. Of course, compiler optimizations can do way more than this to you. So if you're willing to set optimization level large, and you're worried about what the hardware is doing to you, I would suggest a little bit of reflection. Because compilers can really, really, really seriously rewrite your code. And there's the presentation I was talking about there, Victor Paitis. Okay, so another litmus test. This one's a little more complicated. It still has a cycle. So we're doing something to a variable here, another variable, same variable these two guys, same variable these two guys, and same variable coming back around. What this is, it may look a little strange, we have a release-acquire chain with these two processes. So we're doing a write, we're doing a release, an acquire, and a read. So the release-acquire chain should order these, except they're different variables, so how would you know? Well, one way you can know is to write the last variable, have a full fence, so this is a fully ordered fence in the Linux kernel, then read the other variable. And the question then is, really what we're saying is, this release-acquire chain is enforcing ordering within itself. Is it also enforcing order externally to processes that are not involved in the acquire-release chain? And of course, you can get any number of answers. That's a property of your memory model. With Linux kernel memory model, the answer is no. You really can get that stuff showing up out of order. And that is there's a number of, one that's near and dear to IBM's heart, PowerPC. These things are enforced by barriers that do not order earlier stores against later loads. And so, yes, this guy will see that, but the other guys outside, they can see them as being reordered. Okay, why are we doing this? And for that matter, why did Linus Torvalds accept this thing? Formalism is not exactly his favorite thing in the world. Well, we're hoping that it'll be an education tool. We're hoping that it'll help people design better code. We've already had success with new hardware. RISC-V had some a weaker ordering than people expected. And because they had formal models of the hardware, and because we had the Linux-Kernel memory model, we were able to detect that with those formal tools. Say, wait a minute, this code of Linux-Kernel memory model is supposed to give you this ordering, but when we translate it to your hardware, it doesn't. And they're in the process of working out what they're going to do about that. One option is to change the memory model. Another option is to change the barriers they use in their Linux-Kernel implementation. A third one is, of course, is we change the Linux-Kernel memory model. I think they're making the change. They'll decide next month, they say, so we'll see what happens. There are drawbacks. As with most formal things, the size limitations are severe. You get a few processes. If you have something kind of like this and it's maybe 20 processes with just a few accesses per process, you're talking several hours or maybe even days to do the analysis. And it is exponential, which is about as good as it gets usually. Worst case is on the side of it. Yeah?
Can you say a little bit about what we're talking about here? So you've made a model of how the Linux, the model in the form of what? Is it a simulator or a bunch of math, or what are we talking about here?
Okay, so the question is, what is it we did? And the answer to both your questions is yes. What it is an axiomatic model. It's based on something called herd. There's a paper called Herding Cats what it does is it's a sort of a domain-specific language that's designed to express memory models. And so you specify which cycles are allowed or not. You specify what events have what significance, and you use essentially set functions to constrain what orderings are prohibited. And what that means then is that I don't know enough formalism to give you an accurate statement, so I'm going to give you a very rough sort of a thing. Essentially, the memory model, the cat and bell file, the expression, the ASCII text expressing the memory model, is kind of like a set of axioms and some theorems and some relations. And the litmus test is a theorem, and it either proves it or doesn't. That's lying a bit, but...
Okay. And is that the property of Linux, or of Linux on a specific architecture?
Of Linux.
So Linux is supposed to work the same on all architectures?
No. So what this is kind of a least common denominator. So if the Linux-Kernel memory model says this cannot happen, that better not be able to happen on any of the architectures that Linux runs on. On the other hand, if it says something could happen, then the architecture has a free choice. It could let it happen or it can forbid it. So for example, if we go back to the to this slide, this can happen the way the Linux kernel memory model is saying, hey, this could happen. On Power, it really can. On x86, it cannot. Okay. So you have the option of having a given architecture being stronger than the memory model, either because the hardware is stronger, in the case of x86, or because, like ARM, you're using stronger primitives. Yes?
Just to clarify on that point then, so the memory model, I would imagine all that reordering can depend quite a bit on that architecture. So you must probably have to specify that architecture, and only then you get the meaningful answer.
So the question was, do we have to specify the architecture to the memory model? And the answer is no. So there are memory models for architectures, and we make use of those where they exist. And that's the nice case. Otherwise, we're having to read manuals, ask people, or just run test programs. And life's hard when you do that. And those are specific. In our case, what we're doing is think of it as taking, so each of these memories, say we got let's think ahead and wish for a nice world where every architecture has its own memory model, own formal memory model. Now, each of those memory models will make certain guarantees. Okay? And the code of the Linux kernel will map through operations, through instructions, to map onto those guarantees. So we're, I should go ahead. I think I have a slide to this effect. I don't think we're too worried about that. Yeah, okay. So this is your typical hardware memory model. We're on slide 22 if people are having to follow along with the deck, but they can't be because I didn't send it out. And that's your typical hardware model. Languages would have hardware and a compiler. Okay. And what we're doing instead is we're having the architecture code. So the Linux kernel has an arch directory with a little directory underneath it for each of the, I think we're down to 20 some odd. We used to have more than 30 architecture support. There were a bunch of them that were old and didn't compile even. So they said, okay, I'm getting rid of those. And we also have code style constraints. And so what the deal is that we aren't going to worry about this. We have a bunch of different guys here and a bunch of different architecture codes in the Linux kernel. So the combination of each architecture code and the hardware, you could see what happened by looking at the hardware memory model with the instructions specified by the architecture code. And that would give you a set of guarantees. You do the same thing with the next architecture and the next architecture. You ended up with a bunch of sets of guarantees. If you intersected all those sets in some rough fashion, that would give you the strongest guarantees we could make with the Linux kernel memory model. In reality, we make a little bit weaker guarantees because getting an extra few percent of strength in situations that we don't know any use for gives us order of magnitude increase in the size of the model. So we balance between trying to get fairly close to that intersection of the guarantees of the hardware and architecture code on the one hand and keeping the model simple on the other hand. Does that make sense?
Okay.
Go ahead.
So then I'm trying to, you said that the model doesn't scale very well?
It's exponential. I mean, it's way better than it's way better than operational models.
So my question is, in what sense? Like, so if it's proving a theorem, is it like our theorems of the form? If you have up to 15 threads, this holds, and it's the number of threads or something, or
no.
In what sense is it exponential?
One way of looking at it is that you have a bunch of relations. So let's go back or forward or something. Let's go forward because that's not going to help. I'll have to go back. Sorry. I'll make up my mind sometime. Probably change it again a couple times. There. So here we've got a bunch of possible relations. Okay, so this write might or might not have happened before this read. And likewise with these pairs and these pairs. And in addition, so as you increase the number of threads, the number of options, number of ways things could happen increases. And even though it's kind of sort of a theorem prover, it still has to deal with this bigger thing, right? And that still takes more time for it to work out. And you can easily believe, I can easily believe, I don't know about you guys, that as you increase the number of threads, the number of orderings you have to, the number of different possible executions would increase exponentially. And so for me, it's not hard to believe that the execution time of analyzing a given litmus test increases exponentially with the size of the litmus test. And in fact, we measure that, we end up with that. Yeah?
The question that Tool is answering here is, according to the Linux memory model, can this happen?
Yes.
And that's the thing that takes exponential time.
That's right. And what it does is it says whether this condition will always, sometimes, or never happens. And it gives you a list of the states, the possible outcomes, of which there are 8 total possible outcomes. It tells you the ones that can actually occur and whether or not they match this value.
It's a bounded model checking problem, but it's the relaxed memory is really, it's lots of non-determinism, and the model is very complicated and stated in a way that's hard to model check, and so you end up with severe scalability problems even with a couple of threads. So, but yeah, it's basically bounded model checking.
It's actually, if you're dealing with less than, well, it depends on what you're doing, but IRIW, that's the independent reads of independent writes. You have 2 different processes writing to 2 different variables. You have readers reading them in opposite orders. And the question is, do the 2 readers agree on the order the writes happen? Okay. If you use an execution-based model, that's like 14 hours and multiple gigabytes of memory for the state space. With this thing, it's 16 milliseconds. Yeah. But still, it's exponential, so you get to 20 threads, and like, it's still hard.
Exponential in the number of threads.
It's exponential. I don't have a good answer to you, a precise answer, but in my experience, as I increase the number of threads, I get exponential slowdown. If I increase the number of writes independently of the number of threads, I get exponential slowdown. And there's probably other things that matter too. Those are the two that have hit me over the head the hardest. In addition, if you can express something in the language, so for example, locking. We can express locking in the cat language, so the model actually understands locking. On the other hand, you can just use, it's got atomic operations in the model. You can just make a litmus test that says, compare exchange with an acquire, right? And then do a store release to release the lock. Except that that's way, way slower. Okay, so in our experience, putting it in the model, making the model understand the operations is faster than emulating them in the litmus test. But there'll probably be some exception. We haven't hit one yet, though. Read or write along, maybe a test on that. Okay, yeah, good questions, good discussion. Let's see, let's go up. We did this, we talked about that. C11 we're not too worried about here, I think. So about the time I talked here last time, I was realizing we needed some kind of model like this. We had a text file, memory-barriers.txt, that kind of defined, here's what you can get away with. And it was getting large, it was getting cranky, it was getting hard to maintain. I'm the primary author of that thing. Plus, it was getting hard for people to read and understand. And so what I did was I started talking to a bunch of people saying, hey, we need a memory model. Talk to people who have done memory models and various things. And here are my requirements. We have legacy code. By the way, that includes unmarked parentheses, where you say A equals 1, and the compiler can do whatever the heck it wants with it, pretty much. We have a wide range of SMP systems, as we discussed earlier. But we're down to 24 or something of them. We used to be at 31. But still, there's a lot of them. And they have varying degrees of documentation and understanding of what their memory actually does. And we have a high rate of change. We have new architectures showing up. People change what they expect out of an atomic operation, the ordering of this operation, things like that, and we have to be able to keep up with that. As a result, I got a lot of laughter, but no forward progress for quite some time. Until early 2015. So that would have been about 4 or 5 months after I talked to you guys last. So, I did not found this project, actually. I was just agitating for it for a long time. I was at Oxford University, and some kid there was crazy enough to want me on his committee. Since I was there, they had me meet with a bunch of people, including a professor I met through the C++ standards effort. When I walked into the room, the first thing I noticed was a stack of paper. And this paper had been read. I mean, it was coffee stained, dog-eared, folded, crumpled somewhat. There were scrawls all over it, in at least 2 different languages I recognized, right? And I looked closer, and this thing is a printout of memory-barriers.txt, which I thought was really cool. It was the first hard evidence I'd had that anybody actually read the thing cover to cover with the intent to understand it. Unfortunately, it's not mathematically complete. It wasn't designed to be. It was just kind of like somebody runs into a problem. Hey, can I do this? No, you can't stop that. Or, yeah, see right here in the memory-barriers.txt it says you can. Or, well, we don't talk about that, but it seems reasonable, so let's add it to memory-barriers.txt. So it just kind of grew organically as questions came up. Wasn't intended to be mathematically complete. So that's why the professor wanted to meet with me, because, hey, I'm trying to make this mathematically complete model. What is this garbage? So our founder, Sean Alcliffe, University College London, Microsoft Research, is out of date. She, with the last few months, is now with ARM Limited in the UK. And given that I had a whole pile of people with experience in this field telling me it couldn't be done, the question might naturally arise, how the heck did she do this? Because she had a working model at that point. It wasn't quite accurate, which is no surprise given what she was working with, but it did take in code and tell whether or not, with reasonable accuracy, most of the time it got it right, of whether this thing worked or not. Well, she used strategy. One common definition of strategy is kind of a high level what you're going to do. And that's a good definition, and it's useful in a good many cases. But the most powerful strategies usually talk about what you're not going to do. Because if you decide you're not going to do something, that means you stop work on that. You can redirect the effort, the resources, the thought that was going to make that part happen and do something else. Hopefully something more important. And that's exactly what she did. She just got rid of the first requirement. Now, I didn't exactly have a positive reaction to that initially, because, hey, you know, we got a lot of unmarked code here. What's going on? How are we going to deal with it? But when I thought about it, that's actually reasonable. If you're a developer or maintainer with unmarked code, you're letting the compiler do whatever the heck it wants with its assignment statement. Well, I'm sorry, it's on you to work out what the compiler can do. And perhaps what you have to do is generate a bunch of different litmus tests, one for each outcome the compiler might result in, and make sure they all work. You know, it's not an unreasonable restriction. Besides which, I think there's a lot of people that are trusting the compiler way more than they should, and hopefully this will motivate people to mark their accesses. Forlorn hope, I know. Anyway, one big advantage of this is the solution was feasible. Of course, if you're trying to model the compiler, the optimizations they haven't written yet are very difficult to model. We've talked about what they used, but the reason that she wanted me was first she wanted to fill in memory-barriers.txt, but she also wanted to model RCU, my synchronization mechanism, directly as part of the model. And she wanted to find out what that was doing. Now, she actually knew something about RCU because of the C++ work she'd done. And also, we have a paper in 2012 IEEE TPDS that has an informal semantics for it. And Alexei Gotsman and a couple other guys did a separation logic expression of RCU semantics in 2013. So, you know, should be a solved problem, right? How many people have heard of the Dunning-Kruger syndrome? Yeah. Yeah, well, exactly. I hadn't done it before, so how hard can it be? Well, it can be pretty freaking hard, it turned out. Now, Jean has a straightforward process for acquiring the knowledge she needs from a memory model. What she does is she sends a pile of litmus tests. These are essentially questions in litmus test form. So you'll get this tarball in the mail, an email, and each file in tarball will be a litmus test with some strange thing you're supposed to say whether it's happen or not, and a text file where you list the results of all of these. And so I would go and fill this thing out and send it back to her, and I'd usually fairly quickly get back a response to the form, or polite firm response to the form. You know, there is no theory that accommodates a yes to this one and a no to this one, so what are you doing here exactly? This is one example. So this is also kind of a cycle again. And you don't need to know too much about RCU. We've got some RCU things. Synchronized RCU is a blocking primitive. It waits. And what it waits for is any RCU read stack critical section that started first. So here we have our RCU read stack critical section. It starts with RCU read lock. It goes to the RCU read unlock. And if any of these guys happens before this guy, this synchronized RCU has to wait until this whole thing's done. On the other hand, if none of these things come before, it can wait or not, its choice. All right. On the other hand, at the same time, if, for example, this statement comes after this one, so that would be the case when R3 is 1, then we know that this guy in some sense came after this guy because I read the thing that it wrote. Well, then the rest of the statement better not be before that synchronized RCU by the same token. So they can kind of, you know, for a synchronized RCU to return, everything beforehand has to have finished. All the read side critical sections that overlap any preceding code have to have finished. And the other side up, just the other side of that, is that if something comes up later, no part of it can come before the synchronized RCU is called. It's kind of a strange semantics. It turns out to be extremely useful. But there we are. OK, let's actually illustrate the cycle. So we got this, to have this cycle happen, this write would have to be read by this read. And in that case, clearly, this critical section, had part of it came before this guy. So this whole thing has to get done before the synchronized RCU is done. And then this write has to be seen by this read. And if that's the case, this write can't happen before the synchronized RCU is called. And then this write has to be seen by this read. And again, as I said before, synchronized RCU waits for pre-existing readers. Again, a reader starting with RCU read lock, it ends with RCU read unlock. All right, so this is an example she gave me. And let's put it to a vote. I'm going to read off the options, and then we can vote. Option 1, any system capable of doing this should have been strangled at birth. Option 2, reasonable systems really do this. Option 3, there exist a great many unreasonable systems that really do this. And option 4, a memory order is what you give to your hardware vendor. How many people like, I don't know how we're going to collect the people on the phone, maybe you can text your counts to somebody here who can read them out for you, or you can ignore it. I don't know, it's up to you guys, figure it out. Option 1 is any system doing this should have been strangled at birth. How many votes we got for that? All right, yeah. Okay, we got 1 there. Reasonable systems really do this. Going once, going twice, okay. Option 2 gets a big 0 unless somebody elsewhere voted for it. Option 3, there is a great many unreasonable systems that really do this. Okay, we got a few of those, like 5 or 6 of them. And 4, a memory order is what I give to my hardware vendor. Anyway, yeah, we got none on that one as well. Anybody get anything from the other sites? Okay.
No, they don't have video feeds up right now.
Okay. All right. We'll take a local poll then and let them come at the ledger. You know the horrible thing about this? The horrible thing is no matter how you voted, there was a period of time in which I would have agreed with you. Now, number 4 would have been like back in the 1980s, okay, before I did parallel programming. And in fact, what she does, she's got this litmus test. She puts a comment at the front saying what she calls the people she's talking with their oracle. So I was their oracle for this project, saying what the deal was. And that comment says, Paul says aloud since mid-June. June of 2015, that is. So again, no matter how you voted, at some point in time, somewhere in 2015, I would have agreed with you, aside from number 4, where you have to go back to the 80s. And this was a hard one. I went back and forth for a while, but there were some ones that were even worse, where it was RCU and you had a store release and a load acquire, and what the heck happened, right? So towards the end of summer, I was feeling like a really low-class oracle, low-quality oracle. But this really can happen, and this is how. We haven't told the CPU that these have to be in order, so they can reverse them. So we had them reversed here. Before, we had the read, then the write. But let's just look at it from the CPU's point. The write can happen first. At that point, the write can be read by the read. Synchronized RCU has to wait until this guy gets done. But these can be reversed too, which means that the read happens first and can happen before this guy. And then we can actually make the cycle happen that way. So, from here to here to here and back. I'm sorry. Okay, I'm sorry. Let me try to make it better. In fact, let's refer to this diagram on slide 41. And so we see both cases here. Synchronized RCU spans from synchronized RCU to the last wait. And what it has to do is not wait for all of them. It has to wait for all pre-existing ones. So it's very different than a read-arrival lock, where the updater has to wait for all the reads to get done and doesn't allow any new ones to start. Okay. Here, in the most aggressive case, RC read lock compiles to nothing. I mean, it's not just that it doesn't generate any code, it doesn't even make it to the back end of the compiler. And if you turn off debugging and compile for a server in Linux-Kernel, you get exactly that. So this is not theoretical, this is very real. Okay? What that means is the updater has no way of preventing the readers from happening, and also has no way of looking at memory or something aside from looking at their stack traces or something to figure out whether a reader's there or not. So we can't stop the readers from happening. All we really get to do is if a reader is already in flight, we wait for it to get done. So P0 is already in flight when synchronized RCU starts. We have to wait for it to get done. P2 is not in flight yet, so we don't have to wait for it. Does that make sense? Or am I still... no? Okay. This is one of these really weird things where it's simple but really weird. You have to kind of... I don't know, what, take the Laplace transform of your problem to make RCU work with it. I'd be willing to think about it. Yeah, it's easy, but hard to get your head around the first time, and the second time, and maybe the third and fourth as well. Okay, so this thing can happen, and we can run the Linux kernel memory model. This is its output. You say herd 7, you say I want the Linux kernel, and you tell it what litmus test you want. That's its name, and it lists the states. There's all 8 of them, including the one with all ones at the bottom there. And it also says it had 1 positive where the condition happened, 7 negative. And it also says sometimes here, meaning that the condition happened and it also didn't happen. So it happened for 1, it didn't happen for 7. So this can happen, and you have to deal with that when you're writing your code. All right. So what happened was she would send me litmus tests. They'd have RCU, some without RCU, some with both. The ones with both were a nice set of responses. She'd attempt to construct a model, and usually she'd run into a problem and send me more litmus tests to try to work out what the issues were. And what happened eventually, what I finally figured out why I was having so much trouble, there are several implementations, several different flavors, if you will, of RCU in the Linux kernel with very different properties. And so what would happen is she'd send me like 300 litmus tests. And it's not like I'm going to sit down and go through all 300 at once. I mean, that's just not the way my life works anymore, if it ever did. So I go through 20 or 30 of them, then have to deal with something, go through another 20 like that. And so I'd be looking at one type of RCU, and then I'd answer some questions with that implementation in my head. Then I'd have to go off and do something else. I'd have some other implementation in my head, and I'd do the next one. And so my answers were inconsistent because I was looking at an implementation-specific view of a particular implementation at a particular time, different implementations, different parts of the list of litmus tests. And what I needed to do was kind of come up with a platonic RCU, if you will, the model RCU that covers all possible situations. And I did that to some extent. Of course, Jack and I would have done this to begin with in the early 90s, but as you may have noticed, the world's not necessarily perfect at all times. And so we didn't. And what happened is that the same thing happened with RCU that happened with memory-barriers.txt. People would have specific use cases. We would define what happened for those use cases. And we never did really define what happened in a general mathematical sense because there wasn't a need for it. And in fact, that litmus test I had so much trouble with, I have no idea why you would use such a thing, all right? But still, if you want to make a model, you have to be mathematically complete. You have to give answers for that. Okay, what I did eventually is I just started doing a write-up of brain dump of what I knew about RCU and teased out this is implementation specific, this isn't, to try to come up with what's going on. And eventually what I noticed, and also was able to kind of give some rough arguments in favor of, was that if there's at least as many synchronized RCUs in the cycle as there are RCU reset critical sections, the outcome will be forbidden. Otherwise, it's allowed. And in that previous example, we had 2 RCU reset critical sections, P0 and P2, and only 1 synchronized RCU, 1 grace period in the middle. Because we didn't have as many grace periods as RCU reset critical sections, the outcome was allowed. Had we had 2 synchronized RCUs in that P1 in the middle, then it would have been forbidden because we would have had as many. Thing is, in real life, you have 1 RCU reset critical section and 1 grace period. And that's covers almost all the use cases. Anyway, I met with Jod and she called it principal, which is about as good as it gets for a Linux kernel hacker such as myself, with one exception. But she also says it's difficult to express as a formal memory model. Unfortunately, by that time summer was over. She's a prof. Her time was up. And she doesn't assess her. But, you know, she produced the first demonstration of Linux kernel memory model is feasible, even with RCU, and I'm actually pretty impressed with that. She also forced me to come up with a much better understanding of RCU, which you may consider a good thing or a bad thing, depending on your perspective. She designated Luc Marangay as a picture on a sailboat. That's why he has that rope in his teeth. He's a prof at INRI Paris. Also is a major prof, interestingly enough. This was Luc's first exposure to RCU. So that means it was my turn to give him the litmus test to try to demonstrate what the heck it did. And I also tried to implement RCU in litmus test language. which obviously should be possible. I mean, we have implementations of it in the Linux kernel, right? So you should be able to implement in terms of memory barriers and things like that. And these ended up with different degrees of accuracy and solver overhead, the more accurate ones being much more expensive. The weird thing, from my viewpoint, the thing that surprised me the most about this is that the more accurate ones required me to know the value of a load before the load happened. So I had to have a memory barrier up here only if a load down here returned a certain value. And you can do that in these things. They're called prophecy variables. What you do is you just guess. And you just make a random number. You do that just by storing an unrelated process and reading the stupid thing, right? And you say, all right, my guess is 1. I'll do the memory barrier. And then you reject any execution where your guess is incorrect. So you use the exist clause. Well, there's other thing you do if you don't want to have that many variables in your state dump. So that if the guess is wrong, you just throw the execution away and ignore it, which was sort of a surprise to me. So I'd run Luke's models against the litmus tests I had. I'd return a scorecard, and we kind of slowly converged. I even tried writing the rules myself. Luke says, yeah, I see what you're doing, but I don't like your coding style, which is not surprising. I'm a Linux-Kernel hacker. Actually, my evaluation of their style, you see up there, is mutually assured recursion. If we get far enough, we can see an example of that. But his way of modeling RCU, to John's point earlier, required some changes to his tooling. Problem with all this, the thing I really like about Luke is he understands that, in theory, validation is, if anything, more important than it is in practice. And I mean, he told me, hey, I need you to break my model. In fact, we had a little bit of a negation problem at that point. He says, yep, okay, I'll do that. Which, to a Frenchman, is kind of like, yeah, whatever. So I finally figured out what was happening, and I very emphatically said I was going to break his model, and he was sort of modified. I was thankfully able to generate one right after the call that broke his model, so he was okay, but lesson learned. Problem is, though, Luke and I get along really well, but we have very different fields. And communication is always a little difficult. And any miscommunication we have is a potential bug in the memory model. So we needed something else involved in this. But before we get into that, it's worth noting that Luke actually produced the first high-quality memory model for Linux kernel that included a realistic model of RCU. So I had to solve this problem. Unfortunately, I knew a guy named, but before we get there, this is a grad student. He's now got his PhD a month or so ago. And the problem we have here is that, how do we know this matches reality again? So what this guy did was he did a bunch of scripting. And he, I kid you not, created a script that took a litmus test, turned it into a Linux kernel module, compiled it, dumped it into a kernel, ran it, and captured the results, and then told whether or not things worked the way you expected. So this was a really important thing for validation. He also helped Luke add support for this style, which may look ugly to you, but good lord, right? I mean, you guys might like this better, and that's fine. But the Linux kernel hackers are going to like this a lot more because they're used to it, right? And then Luke has an infrastructure to summarize the thing on the web. And what that means, instead of having, he had thousands of litmus tests. I generated like more than 2,000 of them. Luke generated another several thousand. And what it does is it just shows you the ones where it was wrong. So instead of having to look through thousands of results, it just shows you the 6 on the web, which is kind of cool. Anyway, again, we got this communication problem still, right? You can't prove a model correct with testing. And we could just be getting lucky. There are some things that are not guaranteed by the hardware, where it's really, really, really hard to make it break. And so we need, again, a formal bridge between these things. But again, Andrea did some really cool work with infrastructure and scripting to do some initial validation, which was really cool. So I recruited Alan Stern. Now, Linux kernel guys know him as the maintainer of USB HCI, OHCI, and UHCI drivers, which are useful for experimentation. They're out there. I don't know how much use they get normally. But he's done a few more things. He's got a really long publication list. He's got degrees in mathematics in symbolic logic, which is useful for this sort of thing. And he's got a really, I just picked 3 of them. NMR data processing, another guy wrote a book on using nuclear magnetic resonance to find the shape of proteins. Pretty cool. The second one, I'm just going to read the title. I don't know what else to do with it. De novo backbone and sequence design of an idealized alpha-beta barrel protein. Evidence of stable tertiary structure. There you have it. The last one is perhaps more relevant. He was the guy, I mentioned this paper, that had informal semantics, and it also had proofs of correctness, and he's the guy that did the informal semantics and proofs of correctness. And so it seemed like he might have something to add to this. Now, what I'd hoped was he'd critique this model. Go through and find places where it wasn't quite right, get them fixed up and so on. And he did by rewriting it mostly from scratch. On the other hand, I'm not going to go through this in detail. This is an example I told you about mutually assured recursion. These are functions. Each of these things, this, the and, the and, the and. So those 6 things are all functions. And they're all mutually recursive because this is let recursive all of these guys. That's mutually assured recursion. Whoops, that's not what I did it. Okay, there we are. Anyway, I'd have been happy if the RCU read-side critical sections were restricted. So you had to put RC read lock at the very first thing out, and that was the only place you could put it. A bunch of code and RC read unlock at the very end, that's the only thing you could do. That'd work. It would have been done what most people needed. That wasn't quite good enough for Alan. I'm not going to go through this in detail. We don't have time. This thing actually handles nesting. It yells at you if you mismatch. And it also handles multiple groups. So you have RC read lock, RC read unlock, a bunch of code, RC read lock, it handles that. And you have nested inside of them and all that stuff. These 2 guys yell at you if you have them unbalanced. That's the read side. This is the update side. And this is just using recursion. He was actually the cool thing. John and Luke felt they had to modify their tool to handle RCU. Alan was able to just do it within the original tool. And it's just another set of mutually assured recursion that does the counting for you. Just sort of building up from the thing and coming up with all the possible cycles that have at least as many grace periods as read-side critical sections. So 24 lines of code, he's got RCU, platonic RCU totally represented. Pretty damn cool. Yeah.
Do you know what's the tool?
The tool is heard. There's a let's see. When should we be stopping? Noon, right?
Usually around noonish, yeah.
Okay. So yell at me if I don't show you. There's a slide that has installation instructions where you get all this stuff from. It's all publicly available. Okay. I'm going to go through this kind of quickly. Because the relationships are important to some rules of thumb I want to talk about. So this is what's single variable SC. Most machines, Titanium is the exception that proves the rule. If you have a whole bunch of processes doing aligned writes to a single variable, you get SC results. Okay. Titanium can make reads come out of order within a given process. So this is how you express that restriction in herd. So again, these are set functions. We have 3 set functions, com and coherence order. Com is the union of reads from, coherence, and from reads. Reads from is the set of, it's a relation, if you will, and it connects any write to a read that gets the value written. All right? That's the easy one. For me, anyway. Maybe you guys' minds work differently. CO is the order that writes occur for each variable. So what this does is a relation again, and each element of the relation is an earlier write and a later write to the same variable. From read is the one that caused me the most trouble. It's not quite the inverse of reads from. What it is instead is for any read, the relation connects that read to any write that came too late to affect the value read. You can express this in terms of these other 2, which in this crowd might be easier for a lot of you. FR is defined to be the inverse of RF. That's take the relations and flip them n per n. And then follow that with a CO. So this is a sequencing operation. So you take the inverse of RF and you follow with CO, and that gives you the FR relation. PO lock, which is right here. So we get COM as just all the ways that you can communicate, either by reading a variable, by having the writes go in a certain order to a given variable, or the reads coming too early to be affected by a later write. PO lock is a relation that has earlier accesses to a given variable within a thread connected to later accesses to that same variable within that same thread. So if we put those together and then say that relation, the resulting relation, must be acyclic, we've eliminated any non-SC outcomes for accesses to single variables for multiple threads. So that kind of gives you, I could go through this in a lot more detail, but I just want to give you kind of a flavor of the thought process that the language and model do. And the model's around 200 lines of this kind of code. All right. So this is an example litmus test that only has one variable, just the x, and that's all you have. You write it and you read it. You write a 3, you write a 4 in one process, you read it twice in another process. And the question is, can this first read see the last value read? And can the second read see the first value read? And that's what this bug-on statement does. Can R1 be 4, in other words, get the later write, while R2, the later read, get the earlier write's value? So we can look at this relation at a time. Let's start with read from. That one's straightforward. This guy read 4, this guy read 3. There's our F relations in arrow form. Okay, PO lock accesses the same variable within a given thread. So we've got two relations, elements in each relation there, connecting the write to the write and the read to the read. CO is just this piece of the PO lock relation, because we only have the two writes. They have to happen in this order because that's the order they're executed. So there we are. And FR is the weird one. And so this read came too early to do that right. You're going, what? Wait. Okay, remember how FR is defined. We take the inverse of RF, that takes us from here to here, and then we follow CO, which takes us to here. Therefore, that arrow, strange though it seems, really is FR, because that's the definition. And again, we invert RF to go from R2, the R2 read to the write of 3. We follow CO, we get to the write of 4. That's our FR. Okay, once we've done that, once we got all those relations in place, we have a cycle. We start with the write of 4. It's read by R1 read. We have a PO lock down to read once. Then we have the FR back to the beginning. We said that this thing has to be acyclic. Therefore, this execution is excluded. It's disallowed. Okay, that's kind of the reasoning and the way these things work. So it would analyze a litmus test, like it did here. It would look for the links. It would see what cycles formed and see if any of the cycles were prohibited. Okay, let's see here. We're getting towards the end. What I'm going to do is go ahead. We've got this stuff, which is fine. If I do this thing in full bore and do everything and ask all the questions, oops. Yeah, yeah, this will do. It's hours, so we'll do the piece we got. So let me make sure I didn't. Yeah, here we are. Problem with this memory model, there are people who can write Linux-Kernel C code as fast as you or I can talk. They can generate pretty close to correct code just like that, touch typing it. Jad, the lady that started this, can do that with memory model code. I can't do that. I tend to do I'm not the race car. I'm kind of the four-wheel drive, going through the trees. All right. So these guys, though, having to take and turn a litmus test and run through the model is just forget it. It's not going to work. It'll cut their productivity by an order of magnitude. So they liked it kind of, but they really choked on it. The idea of having to use this thing in their day-to-day coding because they want to do this, right? And why wouldn't they? I mean, I want them to do that too, right? It's a lot of code written. So what I did was what we had to do was come up with the rules of thumb for them, and these are the rules of thumb. So we got 3 things, and if they remember these, they'll stay out of trouble. Now, there are things that they would avoid doing that would work, but they're kind of off the beaten track, and these will keep them safe. So we have these RF links and the other links. You only need to worry about RF and other for these rules of thumb. If everything you have in this is an RF link, in other words, one process writes, the next process reads all the way around the circle, then the minimal ordering will work. And that means you can have release-acquire chains, or you could just have dependencies. In fact, you don't need the releases, you just have acquires in the Linux kernel. If you have done even the little smallest amount of ordering that keeps the accesses in a given thread, all the threads safe, you're good. So if you want to make your parallelism go fast, make sure the communication works this way. Okay, if one of the links is not read from, but all the rest are, then you can use release-acquire throughout. So you can have a release-acquire chain. You'll have a non-RF from the end of the release-acquire to the beginning of the release. And in that case, you're good. Just do store release, load acquire, store release, load acquire, and life is good, no matter how long the chain is. If you have two or more non-RF links, life is hard. You need strong barriers, not just one. Even if you only have two non-RF links, you need a strong barrier between each pair of non-RF links. And if you remember back to that funny thing with that's way back earlier on where we had the release-acquire, two processes related by release-acquire, and another with a memory barrier, and I said that was allowed. Well, that's because you had two non-RF links in that thing, and only one memory barrier. If you have more than one non-RF link connecting your litmus test, you need one full memory barrier between each pair of non-RF links. Anyway, so if you remember that, they can type full speed, and that's something they can keep in their head, and we'll see how it works because it's kind of new. But they seem happy with this. Of course, if you're doing something weird and this doesn't work for you, you need something else, there's the memory model. Hopefully that doesn't happen that often. Okay, at this point, I think I'll stop here. Let's see, is there anything else in this that we've... oh, yes, you asked a question earlier, and there's the answer. You can get the DIY tool set. Hurt is part of that at this URL. I'm going to get the slides to Erin, and she can pass them out or do whatever she does with them. There's an install.txt that tells you how to build it. There's OCaml. You need to have that, and it needs to be at least 4.0.2. It may be 4.0.3 for the very latest. And you can download that or install it from distro, which is easier. If you do install it and build it by hand, there's a file that says how to do that. Read the whole file first. Because what it does, I don't know why they did this, it tells you the 5-step process for building it. And at the very end, oh, by the way, if you just do this, it'll do it all at once. I was very frustrated the first time I did that. There are litmus tests, and and what happens is that these litmus tests and the cat files and so on are now in the Linux kernel. So if you go and get the latest Linux kernel, Linus's tree, it's not got to a release yet. It's in, right now we're release candidate 5. If you pick up and do release candidate 5, release candidate 1 or later actually, there's a new directory tool/memory model, and everything's there. The cat files, the vel files, and there's also some litmus tests that you can run on. So it's there, you can use it, and it works out really well. Okay, so I'm going to stop at that point. Other questions, thoughts, suggestions? Yeah.
So what are these kernel hackers have currently been doing? You know, obviously they have some rules of thumb in their head or some practices they've just sort of maybe empirically run across over the years. Do you find now that you sort of have the tool and you can go and spot check things, have they been quite effective in avoiding a lot of these multi-threaded problems, or are there huge classes of things that were illuminated by this tooling suddenly?
Well, for me, there were a lot of things illuminated, but then I was working on it. I've learned a lot about RCU despite having worked on it for 25 years, right? Which was sort of sobering. Peter Zylstra actually did a commit in late 2016 and had a litmus test in the commit log saying, here's why this was broken and we're fixing it and this is why it works, which was pretty cool. I haven't seen too many more like that. We had the RISC-V issue, which was some people digging around, playing with the memory model and saying, wait a minute, these aren't working the way, these don't match each other. So that was kind of cool. It may be a long time before I can give you a statistically valid answer to that question. I'm trying to get people to do larger verification tools, things like scan large code bases and find data race detectors, things like that. So far, they're having difficulty because this is more complicated than they're comfortable with. They need something simple enough they can actually get through the 20 million lines of the Linux kernel source code in finite time.
I guess another sort of way to ask what I'm wondering is, it almost seems somewhat miraculous that the Linux kernel has been as stable as it is making, given that it's so multi-core, multi-threaded.
So I'll give myself an example. I did concurrent kernel programming starting in 1991. And Galois hadn't even published his papers yet at that point. So what I do, right? Well, I kind of knew roughly where the cliff was, kind of, and I made sure I stayed a long ways away from it. All right. So we tended to be rather conservative. We had memory barriers we didn't need, and we had bugs that. The big advantage I had back then, I was working for Sequent Computer Systems. How many people have heard of Sequent? Some people have. Wow, that's unusually high fraction. Maybe this is we're in Portland. Thing was, we only had about 6,000 machines worldwide. A lot of the problems in my code would be due to races. And n equals 6,000. N equals 6,000. Murphy's actually kind of a nice guy. Yeah, everything can happen will eventually, maybe in geologic time. One of the ARM guys told me last year that n now for the Linux kernel is 20 billion. And I did say billion with a B. I really didn't mean 2 times 10 to the 11th power. At that rate, Murphy is kind of a jerk. Everything can happen well, and it can happen pretty freaking fast. There's this IoT stuff, and people are banning about larger numbers. Now, I don't think the Linux kernel gets all of that, because a lot of it's on these microcontrollers that there's no way you're going to fit a Linux kernel. But even if it gets 10% of it, I have this fear that Murphy's going to turn out to be a homicidal maniac. I don't know about you guys, but I feel kind of bad if my software ends up killing somebody, which is one of the reasons I'm interested in this kind of stuff and getting this stuff going and accepted. But so what we would do is, what I would do is I would use locking fairly heavily. If I had stuff out of order, I would assume that the CPU that it could just be arbitrarily out of order. If I didn't have a full memory barrier, I tend not to use the weaker memory barriers much. That it could just do anything. And I made my design handle just arbitrary, or tried to anyway. I'm sure that you could find bugs in it. Arbitrary out of orderness at that time. One of the nice things, this allows me to go safely much closer to the cliff. And also, the rules of thumb allow me to keep reasonable approximation of the model in my head, which is nice as well. Does that help, or?
Oh yeah, makes a lot of sense.
Okay. So yeah, it's kind of. I had to remind one of my collaborators that I was one of the people that actually didn't need the model, since I've been doing current programming without it for a quarter century. But it's nice having it.
Any questions online? No. All right, well, let's give Paul a round of thanks for speaking today.